In all our discussions about the probe size contribution, we have focused on the size of the probe and on the current in the probe. However, there's also an important beam characteristic that we've seen before, which is the coherence in the beam. Now, so far, we have not dealt with coherence before, and in many applications of scanning microscopy, we just care about the size of the focus, so the resolution that we have, and the amount of current we have in, irrespective of whether that is still in a coherent regime or not. But in some applications, we may want to look at coherence, of course for transmission electron microscopy, but also in scanning electron microscopy, we may wish to do diffraction or other types of coherent experiments. So we have seen that for coherence, we have coherence over a specific width of a sample, so the spatial coherence, that is determined by the electron wavelength lambda and 2 times the opening angle of the beam, which we here denoted by alpha coherence, alpha c. So note that this again is the half opening angle of the beam. So we're going to look at this equation in relation to the reduced brightness of the beam. So again, the reduced brightness is given by the current in the beam at the position where we evaluate it over a certain area in a certain solid angle traveling at a specific speed, so a specific potential V. So if we look at this equation, then we see that in this case, if we are looking at a coherent size on the sample, so a size on the sample, a width on the sample in which the beam is still coherent, the area is given by pi over 4 times this coherence length. So this is the xc that we plug in. So as long as we are in a width on the sample that is of width xc, the beam is coherent. So this is the area we need to look at. The solid angle now is given by pi times our half opening angle c, alpha c squared. And if we plug this in to the expression for the reduced brightness, we get PR is I over pi over 4 times xc squared pi times alpha c squared times v. Now from the equation that we have here, we see that the coherence length xc is related to alpha c. So if we plug this in, we get I over pi over 4 times lambda divided by 2 times alpha c squared pi alpha c squared times v. Now we see that in this case the coherence half opening angle drops out of the equation because here it's a squared and here it has a square value. Now if we rewrite this expression and bring the current out, so then we look at the current that we still have in a coherent beam. So the current at which each electron still behaves coherent and in which we could see phase related properties. So we bring all this to the other side and then we get here 1 over 16 times the reduced brightness, and note the 1 over 16 comes from the 1 over 4 and the half squared that we have here, times pi squared lambda squared times the voltage V at which the beam lands on the sample. Now of course these two, the potential and the wavelength, are related. We know from quantum mechanics that if the electron travels at a certain speed, so at a certain kinetic energy, it has a certain wavelength. So from Planck's relations we can get an expression that links these two, and then we arrive at a result that gives us approximately 0.9 times 10 to the minus 18 times the reduced brightness. Now this is a somewhat striking result. So this tells us that if we reduce the current sufficiently to a value that is equal to approximately 0.9 times 10 minus 18 times the reduced brightness, which is a source property, we always can observe coherent effects in the beam. So just reducing the current to this value or lower gives us spatial coherence in the beam. Of course, temporal coherence also plays a role. This is related to the energy spread in the beam. And these two factors now determine whether we can observe coherent effects and do phase imaging or not.